Good afternoon, everyone. Many thanks for you to be here. My name is Pablo Camarilla. I'm a principal at Cisco, and I'm here today with Rita Hui from Microsoft. It's really a pleasure to be here. I've participated in many NOCs in Europe and in Asia, but it's the first time that I'm here in the grand end of the NOCs. So it's really an honor to be here. Now, is the clicker working? Okay. Okay, now. Okay. So the extreme AI requirements have reshaped the traditional data center. What we all knew as the data center has effectively become the front end, hosting all of our compute and inference workloads. And a new fabric has emerged. This new fabric is designed to interconnect the XPUs, GPUs, accelerators, however you call it. This backend network is designed for an extremely high throughput. So indeed, in this network, what we are trying is to avoid congestion. And then on top of it, we have another network that is the storage that we typically often forget about it, but it's very important because the storage is used to connect our storage systems like BAST with the GPUs that is used in the case of the AI training first to load the data, but then also to take these periodic snapshots. Now, today, I really want to focus on the backend, but in 2 minutes, I want to very briefly point you to this presentation from Alexei from Nebius. At Nebius, they had a classic design where they were running EVPN VXLAN in the data center, and they were stitching it with an L3 EVPN with segment route and MPLS in the WAN. So basically, the customer traffic coming from the VM would arrive to Nebius network on the cloud gateway, and from there they would do a VXLAN encapsulation that would go all the way up to the DCI, where they would basically remove the VXLAN header and impose the MPLS label stack all the way up to the border router. They have worked on a new design that is based on SRv6 end-to-end converge. So basically, on the cloud gateway, you do the imposition of the SRv6 header that goes all the way end-to-end. And this comes with various benefits, as for example, you can completely forget about the IPv4 loopbacks in the VXLAN network, which is something that is still common across many vendors. You remove all of the stitching functionality on the DCI, which at the end is just additional cost and additional complexity of removing the VXLAN imposed in MPLS and vice versa. And then more interestingly, you can do interesting things for service chaining, as it was the Nebius case, where basically they were wanting to have all the traffic routed through a firewall, and because on VXLAN you don't have any traffic engineering ability, they could only place this firewall near the edge, the perimeter of the data center, and it resulted in a very large cluster of stateful firewalls, which was very difficult to scale. And so they basically, with segment routing, you have traffic engineering abilities, and so you can have smaller clusters distributed across the network. So I'll leave you there the recording from Alexei. If you have any question, don't hesitate to reach him. He's super friendly, as well as an IETF draft. Now, let's focus into the backend. What makes training special? The training workloads involves processing vast amount of data over a period of weeks or months. The processing itself is iterative. It's divided into many iterations or many epochs, and basically on each one of these iterations, you are going to perform the computation based on the gradually updated incoming data. What this means is that the GPUs, they are going to communicate very often in between them. In reality, they are at the end of each one of these iterations, they will need to communicate and they will need to synchronize the results in between them. So basically, if we have some GPU that is slower to synchronize with another because we have some network degradation, what this means is that all of the GPUs, they are going to be sitting idle waiting until the next iteration can start. The traffic from these GPUs, what is going to result is into traffic that is going to be extremely synchronized and extremely bursty. So actually you can see that on the diagram from the top right. That is a report from Alibaba that they disclosed at the SIGCOMM last year, where basically you see the traffic from the 8 NICs, and you see that this traffic is starting almost at the same point in time, it's stopping at the same point in time, and the traffic is going to the full link capacity as these were 400 gig NICs. Okay, so basically it's nearly a binary on and off nature on this traffic. This traffic has, the number of flows is going to be relatively smaller compared to the traditional data center, which will turn into some issues or some challenges, as we will see later. And basically the traffic is also predictable because all of the AI job is orchestrated in advance, so we know which GPUs are going to which GPUs, okay? And there is one big caveat, that is that any sort of degradation or any sort of failure in the network is going to be extremely, extremely costly. Okay, it's going to be extremely costly first because if I have, if the network is slow, what it means is that the GPUs are going to be sitting there on idle state waiting for the next iteration to start. But further on, if I have a critical SLA degradation, what will happen is that my job will crash and I will need to go to the last snapshot, maybe 15, 30 minutes ago, and I will need to restart from there. Okay, and actually Meta, they actually reported during the SIGCOMM 24 that during the training of Llama 3 for the 406 billion parameters, it actually took them 6,000 GPUs over a period of 54 days, and they had 419 unplanned job interruptions. Okay, so that's roughly one unplanned interruption every 3 hours. So this is something that is extremely costly, and out of these numbers, 8% of the issues were caused by the network. So we want to completely try to avoid this. Now, ECMP is extremely fragile. Okay, in the AI backends, the number of Q pairs, which is the fancier domain name for a flow, the number of flows or Q pairs is going to be relatively small to a traditional data center. And ECMP is going to be extremely fragile when we get multiple flows hashed into one single link, whereas we have other unused link. Because basically this will cause queue buildup, this will cause congestion, this will cause packet loss, and then eventually go back and retransmissions, which is something we want to avoid. I'm sure all of you have heard about the different congestion issues, about incast, outcast, in-network congestion. For example, incast is very, very common when we do the overreduce operation. So basically all of the GPUs, they have computed their gradients and you need to average them. So you are going to send all to a target GPU that is going to do this averaging. And basically from a network point of view, what this means is that everyone will be sending towards the same switch downport towards the destination GPU. And so basically we will have congestion, packet drop, and the GPUs will be waiting. Okay, now the industry has been really scratching their head around how to solve this. And this is one slide that I really like because it summarizes all of the different efforts that the industry has been working on. Okay, so I've divided it into two different families. Okay, so I have the switch-based solutions where basically all of the intelligence is done from the switch point of view. And then we have the NIC-based solutions. The NIC-based solutions are solutions that basically they take the assumption that the network does nothing, just classic 5-tuple ECMP load balancing, and they try to solve all of the problems from the NIC. If I go very, very quickly through the different solutions as a reminder, basically from the switch base, the first one is the load hour stateful flow spray. Some people also call it dynamic load balancing. Basically, the first time that I see a packet for a particular flow, I'm going to make a decision and I'm going to stick to this decision for all of the remaining packets of that same flow. Okay, and this may be based on the local or remote congestion. We also have a static interface pinning. So basically this works for two-tier clause, and basically on the leaf device, I'm going to set a policy where the traffic from a particular GPU is mapped to a specific uplink towards the fabric. We have flowlet, where basically we try to find gaps in terms of time in between packets, and basically we batch the packets into this notion of flowlets, and each one of those flowlets or batch of packets is going to be sent through a different link. DSF, disaggregated schedule fabric, Meta has partially deployed it in some of their clusters. I'm sure tomorrow they will talk about it, but the key idea is to build a lossless fabric by doing a credit-based system, pretty much like what you will see in a chassis or what we see in InfiniBand fabrics, and obviously you have the challenge of scaling that. And then we have packet spray. Packet spray, what it's referring is about making individual forwarding decisions for each one of the packets, even within the same flow. Okay, so packets belonging to the same flow, it may go through different interfaces. Packet spraying can be done either from the NIC or from the switch. In this case, what we are talking about is about doing packet spraying from the switch. Okay, and packet spraying, it can be done either randomly, or we can do adaptive, what is known as adaptive routing, that is basically to spray based on the local or the local plus remote congestion status. Packet spraying done from the switch in the case of adaptive routing, it does provide some good results. However, it causes some issues, as you see, for example, a packet with the same header in different places of the network. So from a manageability or debuggability point of view, it's kind of complex. Okay. Then, if I move very briefly to the NIC-based mechanisms, basically, as I was mentioning earlier, the key idea of the NIC-based mechanisms is that the fabric is just going to perform classic ECMP load balancing. And so the first mechanism that you have is oblivious packet spraying. Oblivious packet spraying is packet spraying done from the NIC. And the way that is done is by playing with what in the ultra Ethernet they call the EVs, the entropy values. So basically, the NIC is going to play with the UDP port numbers or with the IPv6 flow label to get packet routed through different paths in the fabric randomly. Oblivious packet spraying, almost always has to be deployed together with packet trimming. Packet trimming, for those of you that don't know, it is basically one of the new innovations that, in my opinion, is one of the nicest from the ultra Ethernet. And basically, it's a mechanism implemented by the intermediate switches in the fabric that whenever they have congestion, instead of taking this packet and dropping it, what they do is they actually trim all of the payload. They mark this packet as trim. They are going to change the DSCP so that it goes on a higher priority. And either they send it to the destination in what is called FTD, forward to destination, or back to the source, BTS. Okay. And so packet trimming, what it really helps, it is helping the source or the destination to know that this packet has been lost and this packet has to be retransmitted. Okay, so it's a fast loss detection mechanism. Okay, it only works for congestion, so it does not detect whenever we have network failures. Okay, so for example, if we have an interface down and the packet has been lost, it is not detected, but still it's going to deliver very good results for whenever you have congestion in the fabric. Now, the alternative to oblivious packet spraying is going to be multipathing. Multipathing, it has been proven in deployments and academically that it delivers very good results. And the key idea of multipathing is that we are going to use multiple paths through the fabric. And basically, whereas in oblivious packet spraying, the source NIC didn't have any state for each one of these paths. In multipathing, I will be preserving some state about basically how each one of these paths is performing. Okay, so basically, I will, for example, be taking 5 different entropy values, and I will be monitoring how each one of these 5 entropy values is performing. And based on that, I will be performing load balancing actions. Okay. This is orthogonal to the fact of whether we have one congestion window for the entire flow or whether we have multiple congestion windows. But the key idea is that from the source, I will be using different paths and I will be maintaining a status about each one of these paths. Now, the most simple way to do multipathing is by playing with the entropy value. Okay, so the whole idea is that I'm going to use, for example, the entropy value is 100, 200, 300, 400, 500, and I'm going to be sending packets on these 5 entropy values, and I'm going to be monitoring the performance of each of these 5 entropy values. And if I detect that there is a significant performance degradation, either with the SCN, the packet trimming, or just by monitoring the round trip time, I will be changing one of these entropy values. Okay, so this is in essence what reps or, for example, SRAC are doing. Okay. The issue with these approaches is that when I change from one entropy value to another, it's basically a probabilistic action. I do not know that if I change the entropy value from 100 to 700, that effectively this packet will take a different path through the fabric. Okay, maybe it's hashed on the same exact set of resources, and maybe it goes again through the congestion. Okay. So that's why instead of this probabilistic approach, one of the alternatives that was explored, it was basically to try to predict how entropy values are hashed through the fabric. Okay, so basically you ask your vendors what is the hashing algorithm that you have on each one of these routers, and you try to predict how the EDP port number 700 will be hashed through the fabric. But obviously this also comes with some issues, as for example, in the moment that you have a change in one of your ECMP groups, because for example you have a link failure, basically what will happen is that your ECMP group will change from 64 members to 63 members, and then all of your hashing predictions will be broken. So in order to solve this, what you need is to have a sticky or consistent load balancing, which obviously also comes at a cost. So basically, today, most of the solutions that are centered from the NIC are centered around trying to use the entropy values. Okay, but there is a different way of doing things from the NIC. And that is basically the deterministic option that we have with a strict source routing. Okay, so the whole idea of source routing is to give control to the source. Okay, so in this case, we are going to give control to the source GPU, or better said, to the source NIC, to select how each packet has to be forwarded through the network. So what we will do is that we will encode into the packet header the list of nodes or links that this packet must traverse. Okay, and if you remember in source routing, we have loose source routing and a strict source routing. Here what we are talking is about a strict source routing. So in this packet, we are going to enumerate the exact sequence of links that this packet must traverse. What we get with this is two things. First, we are avoiding hash collisions. We are avoiding hash collisions because we are avoiding ECMP. We do not have any ECMP in the network because the source is going to explicitly state all of the sequence, all of the set of links that this packet must traverse. And the second, this is quite interesting, that is actually that we do not need to wait for any state propagation through the fabric. So if you have any link failure, if you have any congestion, you would typically have to wait either for BGP to converge or for some form of controller to propagate the status through the fabric to change the path. And this is not the case, because with source routing directly from the source, if you want to change the path, you just change the list of instructions that you put in the packet header. So every change is done directly from the NIC. Now, today, if you want to build a source routed solution for the data center, you will do it, you will for sure want to do an IPv6 native solution. And the way of doing it today is with SRv6. SRv6 is widely supported across all of the different network vendors, is widely supported across all of the merchant silicon, so it doesn't matter if you want deep buffer, shallow buffer, you have it on Cisco Graphene, you have it on Broadcom Tomahawk, NVIDIA Spectrum, you have it. You have it on a broad range of open source stacks, and from an IETF point of view, it's fully standardized. Okay. And side note, at the end of the presentation, I've left a few slides with additional information. One of them is referring to this, to all of the IETF drafts and RFCs, so you have it on the appendix of the presentation. Now, with a source routed fabric, you have many benefits. For example, in any fabric, you typically need to have a dynamic routing protocol that is going to build the reachability in between the different nodes in the fabric. If I have a link failure, typically for BGP to reconverge, it might take ranging from 10 milliseconds to even a second in some of the most dramatic cases. Still, if I have, for example, a link that has gone down, if I assume that it takes 10 milliseconds to propagate this link failure and to update the ECMP group on the feed of the neighbor, if I assume I have a 4 kilobyte MTU and a 400 gigabit link, what this means is that I will be dropping around 120,000 packets, half gigabyte of data plus all of the related congestion control packets. So this is something that with SRv6 we can avoid, because SRv6 with a strict source routing is not ECMP exposed, but also what it means is that it can be deployed on a statically provisioned fabric. So you do not have dependency on a routing protocol, you can just simply have a fabric with a static routes, and whenever you see any failure, you just simply change the list of segments from the source. Another key benefit is virtualization. If I have a fabric that is shared in between multiple tenants, I want to obviously have this tenant separation in between all of the different GPUs. We've seen some hypervisors that are basically writing their own plugins to, for example, push a VXLAN header right from the NIC. This is going to eat into your MTU. This is going to burn cycles on the NIC DPU to build this VXLAN header. You don't need it with SRv6, it's just one segment in the header. And more importantly, you can also have resource isolation in the fabric itself. So if I have a fabric that is shared into multiple customers, maybe I don't want to have the spines being used by all of the different customers, because maybe one noisy neighbor is going to eat into the resources of another. So there are several ways in which I can build this isolation. Maybe one of them is with DSCP, but you have another one that is with SRv6, where you can actually provide some form of hard slicing between the different tenants. Now, very quickly, we are all seeing how up to now we have focused on the scaling of these clusters, either with a scale up or a scale out. But we are seeing that due to the power density requirements, the only way of scaling these AI training workloads is basically by going into the region and going beyond a single data center. And the minute that we start looking into how we go beyond one single data center, we very quickly realize that we will have a traffic engineering problem. Why? Because we see links where first the links are more expensive, the capacity is more scarce. We see, for example, that there are a lot of SRv6 because at the end out of a data center you just have physical conduits with all of the fiber. We see that, for example, we have direct connectivity in between data centers to avoid going to the regional hub. So we see that there is a very big traffic engineering requirements when we look into into how to scale beyond a single data center. And here, before I pass it over to Rita, I think it's very interesting to have this reference from Alibaba that they have deployed the SRv6 for the DCI for the connectivity in between the data centers. So they did an awesome presentation at OCP this year where they explained their design, and I think that's very interesting. And so now, with that, I would like to hand it over to Rita, who is going to explain how we operationalized SRv6.
Hey, thank you, Pablo. So at Microsoft, our AI superfactories rely on an intelligent data center fabrics that ties thousands of GPUs together to enable the world's most advanced AI training model. So then I will highlight the core requirements that shaped our network solution design. Number one is that the solution must be cost-effective and scalable. So that means we want to avoid proprietary technologies and relying on open standard-based approaches. And as Pablo mentioned, the traditional passive hash-based load balancing mechanism suffers from low entropy problem and resulting into low utilization. Therefore, we need more active traffic engineering to steer traffic intelligently. Also at the scale, network failures are inevitable. So this makes fast failover a critical requirement to maintain the reliability. And then finally, multipath transport coupled with fine-grained control will be able to give us a more efficient utilization of the network bandwidth. And yeah, that's why we would like to have more fine-grained path control. So together, these drive the needs for an open, resilient, and traffic-aware design. So in order to meet these requirements, we use a dedicated backend network for the training of the AI traffic, and then we use SRv6 to carry the traffic from one GPU server to another. And we like SRv6 for several reasons. And as mentioned, it actually provides the fine-grained control. And also, very importantly, it's a standard-based source routing protocol. And then it supports the detailed path enumeration using the microSID, which is crucial to define the traffic path through the network. And then the number three is that it enables tight couple with the AI workloads flow scheduling at the source so that users could determine how they can better optimize the network performance. And then finally, with the integration of more advanced transport protocol at the GPU host, then this solution can support the detection and responding to network failures or congestions without waiting for control plane convergence. So I'll give an example here. In a two-layer topology, we use T0s to represent the top-of-rack switches connected to a NIC server, and then T1 as to represent the leaf switches connected to the top-of-rack switches. So in a two-layer topology for the AI backend network, the SRv6 tunnel will have 4 nodes. The first node will be the source T0. The second node is the T1, and then the third node is the destination T0, and then finally the last node will be the destination NIC. As you could see, applications can pre-calculate all the possible paths from one NIC to another. And then, let's say when there is some conditions, network conditions detected at the 01T1 node over there, then the NIC will react by updating the second node in the uSID list to 02T1. And then subsequent packets will be immediately redirected to a pre-computed alternate path. And then another benefit here is that since this is only 4 nodes in the path, there is no need for SRh, and then the SRv6 packet, the packet length will be more optimized. And then the other is that benefit is that when there's a need to build more GPU servers, then we add. And then if you need to add more T0s and T1s in the network, there's actually no change in the packet format or the encapsulation format, right? So everything, because the path stays as 4 node here. So that's why we like this design. And then finally, in order to simplify the operations, we use static configurations. The seeds are statically configured in all the switches, and then also static routes are used for sending the traffic to the neighbor nodes. So for example, here in this example, let's say the switch A has a path of B, C, D, E, F, and then the switch B, after it gets the packet, and then it would does a lookup and sees that the first USID in the path matches its assigned USID value, then you would quickly do it will be able to continue to the shift and forward operation on the USID list, and then the path becomes CDEF, and then it's able to quickly forward the packet to the next node. Okay. We use SONiC in Microsoft. SONiC is an open modular network operating system that is designed to support very large-scale data center fabrics. In order to support the SRv6 static UC implementation, we just need to add 2 tables inside SONiC. We call it SRv6 myLocators table and SRv6 mySys table. The myLocators table will store the locator value assigned for each SONiC device, and then the mySys table will hold seed to behavior mapping. And then there's the services or SDN controller. It has a full view of the topology. It would assign the locator values or USID for every single devices in the network, and then it would push to the config DBs inside SONiC. And then there's BGP config D daemon in SONiC that is listening to the configuration changes, and then you will be render the configurations, the SRv6 configurations accordingly into the FRR, which is the BGP routing stack being used in SONiC. And then finally, these configurations will be propagated down to or be programmed into the hardware switch by the switch abstraction interface SI. That's another standard hardware abstraction interface API. So this slide gives a very quick snapshot of the SONiC support in SRv6 support in SONiC. From a functionality standpoint, SONiC supports all the building blocks needed for production deployment for SRv6, including microseed behaviors, the static seed provisioning, traffic steering, and then alongside with the EVPN and FRR routing stack evolution. And equally importantly, this work is driven by a multi-vendor community across cloud, telecom, enterprise environments. So this validates the interoperability and the operation readiness. So just a final acknowledgement to the key members for these contributions as well, and besides two of us.
Hello, my name is Kemal, and I'm from Cisco Thousand Ties. Thank you for this fascinating presentation. One question, given the static nature of the configuration that you are pushing here, how do you, and how the fabric reacts on the link failures, congestion, and stuff like that, how quickly it converges to alternative paths?
So actually, that's kind of echoes what Pablo earlier mentioned, right? So there is the, for example, packet trimming will be one of the key protocol, right? So that the host, the source or the destination will be able to detect that the network condition or the path condition actually has degraded. So in our scenario, or AI networks, our customers actually has a very hard requirement into how they can monitor the performance, and then control how they wanted the AI traffic to be able to go to the best optimal paths. Yeah. So then actually there was. I think this could be debatable, right? Like, for example, static routes, if there's a link failure, then the static route is no longer valid, right, for example. And that is true, but because of these fast congestion or degradation detection mechanisms, it's actually relying on the applications to quickly reroute it to the alternate path. And the alternate path is actually already pre-computed, meaning, let's say, the user list are all pre-computed already. So I think it's a little bit like the, for example, fast reroute, those kind of things, right? There's actually multiple hot standby paths already available. Yeah.
Thank you very much.
Hi. Thank you for your presentation. I do have a question. Today, do you explicitly know if your packet trimming is due to an incast? Or are you just tracking and saying all of the path seems to indicate it's congested, and therefore it must be an incast?
No, I think that one we just follow whatever the standard being specified for the packet trimming. So either send to the destination or send to the source.
Okay, but today you don't explicitly have knowledge that the trimming happened at incast, kind of like the last hop location. Meaning if it happened there, it wouldn't make sense to load balance.
It could be anywhere in the path, right? Yeah.
Meaning if the congestion happened because of incast, then switching path would not necessarily help in that case. I'm just kind of wondering if that knowledge is explicit, or it's just basically all the path coming back indicate it's congested.
I think when you design a network, you probably wanted to make sure that there is no it can support the worst case scenario, right? So I guess there will be alternate path that is better than the path that is congested, right? So yeah,
right.
And also there should be also PFC, those types of handlings over there as well, so that there is a back pressure for the source to kind of slow down a little bit. Yeah.
But so basically, to add to what Rita is saying, today there are several signals that you receive at the source to know that you need to change the path. The signals that are most typically used, basically the round trip time, the ECN packet trimming. With packet trimming, you do not know where, or you do not know what is the congested resource in the fabric, okay, going to your point. And I think this is one of the key things that over the time we want to change.
Right.
Also, and also that packet trimming is also typically done forward to destination. Maybe sometimes it makes more sense to send it back to the source. But the whole point is to leverage all of these signals that the network is giving us, and to have a fabric that is fully statically configured, and so that we have the fast reaction time from the source. Basically, instead of having to rely on any dynamic routing protocol on the fabric, that is obviously much slower. Okay, because for example, the BGP reconvergence is going to be few milliseconds, whereas any signal that we get right at the source, it will always be in the range of microseconds. So it will be much faster. And then the key point is that basically with SRv6, you change the path immediately without needing to propagate anything through the fabric. It's just a behavior on the NIC where you just change from one path to another one, and the paths are pre-computed as Rita was explaining.
Okay, thank you.
Thank you.
Navendu Sinha from Extreme Networks. Well, thank you very much for this presentation. I think it's adding on very well to the other talks as well. One clarification, right? In your slide, when you talked about the backend AI training traffic, you mentioned that it is predictable. You mentioned that the AI backend traffic is pretty predictable. Now, clarification on that, right? That predictable for who? Is that from a NIC perspective? Is it from the compute perspective or the network perspective?
So basically, today we are not using that predictability nature. In the slide, I was referring that it's predictable because you orchestrate the job at the beginning, so you know the graph of which GPUs will communicating to which. That characteristic, it may be interesting for some applications. In the case of the use of SRv6 here, we are not using that predictability, basically.
Because predictability would lead to, let's say, like some sort of a schedule. Right? So that's what I was
Yes.
referring to, right? That
Yep.
okay, well, if it is predictable, it can be a schedule. Right? And hence, perhaps congestion can be avoided.
Yeah.
Second question, right, around this is in some designs that, like, let's say, like in a talk that was done earlier, there was the architecture that was referred to was NVIDIA's rail architecture, and what you guys talked about here seemed to be getting the NIC to peer with 2 TARs, right? So that seems to be slightly different. So could you elaborate on that choice?
Okay, so I think the design of how you build your network, if you use the rail design, if you use multiplane, it's orthogonal to the usage of SRv6. SRv6 can be used regardless of how you build the fabric, and it has benefits regardless of how you build this fabric. And then in the specifics of the deployment of Microsoft, if you want to elaborate more, Rita, on rail.
You mean NVIDIA is using?
There is the NVIDIA prescribes a rail design, right? For so like, but in your design, when you in the architecture that you guys shared, you showed that the NIC card is pairing with 2 TARs.
Well, it's just no, it's not necessary 2 TARs, right? It's just an example. Yeah, okay. It doesn't reflect the actual production design. Yeah, I think it's very flexible and based on. Usually the objective is to best use the maximum number of ports you have, and then how they map to the number of NICs in the GPU server, right? Yeah.
Okay, thank you.
Thanks for the presentation. This is Quincy from Cloudflare. Is the TE, does it self-revert over time? Like, let's say the source detects congestion and then it picks up one of like the other uSIDs in its list. Does it revert back to its initial one, or does it just repeat the cycle if it detects congestion again? Does that make sense?
Can you repeat?
Yes. Can you elaborate more?
Yeah.
How does it revert?
Yeah.
So when a backup path is enabled, how does it revert back to the original primary path?
Oh.
If at all.
Okay, got it. It may or may not need to, right? Yeah, I mean, if things are working, I just use it as a comparison or analogy to explain that, right? But in this design, there is actually no, not necessarily like a best path per se, right? But it's just that there could be multiple good paths per se, right? Because if you see that, it's actually a very everything is actually forward-looked, right? In a steady state, or if everything is up, so then, I mean, you just continue to use the alternate paths once you switch there.
So there's no like state tracking.
But then coming back, right? Let's say if the link is coming back up, now you actually have one link that is repaired, and then a network link that is actually underutilized now. So then going back to the original design principle, it can then basically update the flows to get it back to go back to the first path. Yeah. But then it's not necessarily saying that those alternate paths are not used anymore. It could be still being used for the other flows. Yeah.
Thank you.
Thank you so much.